Welcome. Today we will discuss the basic features of a population. A population is generally a group of individuals or organisms of a particular species occupying a particular area at a specific time. It may be, it can be explained by its various inherent characters or attributes. And we must know all these characters to understand its various interaction and how they establish within a particular area. Firstly, this is density, then dispersion, then age structure, natality, mortality, etc. In the age structure, and firstly, we'll discuss what actually a density is. A density is defined as the number of individuals per unit area or per unit volume of the environment. So, a density can be explained either by number or by its dry unit. So, a population density may be of two kinds. First one is known as the crude density, and the second one is known as its ecological density. How we can differentiate? To understand this, crude density, it is the number or the biomass or dry weight per unit of total space, and ecological density or the specific density, it is the density, number or biomass per unit of habitat space, that is the available area or volume that actually can be colonized by the population. Like some plants, like Cassia tora and Ophlymase brunamali. All this, they are actually prefer some specific type of area. Like Cassia tora, usually they prefer shady areas. And if we consider, they are also found in other lighted areas or non-shady areas also, but usually they clumped or aggregated in the shady areas. So if we consider the density for the shady area only, then it yields the ecological density. And if we consider the shady as well as the exposed area or the lighted area, then it yields the crude density. The other important attribute of the population is known as dispersion or their spatial distribution. To explain this, at first, I'm showing a rough diagram. Just follow this. Each and every species in a population they follow a specific pattern of their dispersion. This is a particular pattern. This is a particular pattern, and this is also a particular pattern. The first one is a regular dispersion, regular one. They are uniform also. The second one is random. The third one is clumped or aggregated in nature. So, in case of regular dispersion, they follow, although it is very much rare, here the individuals are more or less spaced at regular and equal distance from one another. We can manage this in a cropland, as here we are very much determined how much uh, distance we maintain to propagate a plant from one angle. And in random dispersion, there is no specific pattern. Here, the position of one individual is unrelated to the position of its neighbor, and this is also relatively rare in nature. And the third one, already I mentioned, the clumped or aggregated one. They prefer to aggregate, and they prefer to associate with each other and aggregate it into patch or patchiness with few or several individuals. Such aggregation may result from social aggregation, biotic interaction, family groupings, or other biotic interactions. And obviously, the environment play an important role for this patchiness also. Then we go through the age structure. What is the age structure? In almost all types of population, individuals are of different age. Okay, so we can categorize the age into as the pre-reproductive, pre-reproductive category, then the reproductive category, then the post-reproductive category. So, there's three. The proportion of individuals in each group is called the age structure of the population. The ratio of the various age groups in a population determines the current reproductive status of the population. And from an ecological viewpoint, there are three ecological ages, already I mentioned, the pre-reproductive, reproductive, and the post-reproductive. And depending on their proportion, they form three special type of population and structure. The first one explained by young population, the second one the stable population, and the third one the decline population. But how? In case of young population, just follow this. The pre-reproductive pattern is maximum portion, then the reproductive, and the post-reproductive one is lowest. And they are growing, young or growing. The second one, it forms a bell-shaped population. Follow this. The pre-reproductive portion reduced from the previous one. The reproductive portion increased, and the post-reproductive portion also reduced. This bell-shaped population is known as stable. And the third one, represented by the least proportion of the pre-reproductive or the young population, then reproductive population increased, and the post-reproductive population also increased to maximum. And they show a declining population. So in case of declining population, the post-reproductive portion increased maximum. So by using this, we can categorize the population into three types. Then the birth rate or the natality. Population increases because of its natality, and this character, that is the natality, is much more important than mortality, and we will study the biotic potential solely on the characters of natality, although we use the equation birth rate by death rate into 100 to explain the biotic potential, but in this equation birth rate is much more important than the death rate. Similarly, mortality or death rate means the rate of death of individuals in the population. Then we have to study the vital index and the survivorship curves. A birth-death ratio into 100, that is birth by death into 100, this actually indicates the vital index. For a population, the surviving individuals are more significant for that population than the dead ones. The survival rates are generally expressed by the survivorship curves. A survivorship curve is a graph showing the number of proportion of individuals surviving to each age for a given species or group. There are three types of curves. So, if we develop the curve like this, the y-axis indicating the percentage of organisms surviving to the x-axis, which indicates the time or age group. The type 1 curve, this one, is the most convex one. They show a late reproductive episode in their life. They are much more stable. They can withstand environmental fluctuations. They can maintain their biotic potential much more effectively, and represented by humans. The type 3 curve, the concave one, they show an early reproductive episode, a bigger clutch size, less understanding and less interaction with the surrounding environment, less parental care or parental care nil, it is better to say. They form type 3 type of graph, like very small insects, etc. And the mid one, type 2, they form a stabilized approach and represented by some songbirds and other organisms, and some fish also. In this case, I want to introduce two special terms which we have to know. First one is known as the interoperous, and the second one is known as similparous. Interoperous and the similparous. Okay. In case of interoperous, which is very common for type 1 curve, and they have multiple reproductive episodes. Reproductive episode in their life. And in Semmelpers, they have single reproductive episode. Single reproductive episode. They actually develop the type 3 curve or represent. And interparous organisms, they indicate type 1 curve. Just check the graph. Type 1, they form interoperous type of pattern, and type 3, they form simulparous type of pattern. Here we also get another term known as clutch size. Clutch size. This actually indicates the number of organisms produced or formed in per reproductive episode. So, in type 1 type of survivorship curve, they have a smaller clutch size, and type 3 organisms, they have a larger clutch size. Then the biotic potential, or usually known as the reproductive potential, that is the inherent power to grow or inherent power to reduce. This is the most important line. So that when the environment is unlimited, that is, there is no restriction, there is no carrying capacity, the specific growth rate, that is the population growth rate per individual, becomes constant and maximum for the existing condition. This value of the growth rate under these favorable conditions is maximum, is characteristic of a particular population age structure, and they develop the exponential type of growth. Anyway, the biotic potential can be explained by R equal to B minus D, where B is the birth rate and D is the death rate of that organism. But here also, the birth rate is much more important than the death rate. The overall population growth rate under unlimited environmental condition, small r, depends on the age composition and the specific growth rate due to the reproductive component age groups. Thus, there may be several values of R, or usually known as the intrinsic rate of natural increase. So here we can mention the biotic potential, or R, equal to intrinsic rate of natural increase. Then by knowing this, we can understand their population growth pattern also. And species differ widely in the number of young produced each year, in the average age to which they live, and in their average rate of mortality. When sufficient facts about a species and their life tables are known, and this life table can provide their virtual statistics of their life expectancy and their other biological characters. Now, the population growth curve. Usually, there are two types of growth curve. First condition, when there is environmental restriction or environmental resistance. In this case, they show or they develop a ascending or sigmoidal growth curve. And the second condition, when there is no restriction, the population can grow indefinitely. They form a J-shaped curve. So these two things can be explained by these equations. For the first one, that is for sigmoidal growth curve, we can explain this easily by Gn by dt equal to Rn. Here, the Gn by dt actually indicate the changes in population per unit of time, changes in population per unit of time. The n is the population size, and small r, the intrinsic rate of natural increase. Intrinsic rate of natural increase. So this equation, that is dn by dt equal to Rn, actually indicate a condition where there is no environmental resistance or environmental restriction, and it forms a J-shaped curve, or this curve is known for exponential growth. And there is also another equation explained by Gn by dt equal to Rn into k minus n by k. We all know that dn by dt, the changes in population per unit of time, capital N, the population size, n, the population size, and what is this k? The k is the carrying capacity of that particular population. Carrying capacity. So this equation, that is dn by dt equal to Rn into k minus n by k, this actually establishes a special condition of a sigmoidal curve. That is, when there is environmental resistance, a few organisms are introduced in an area, the population increases in a very slow rate in the beginning, positive acceleratory phase or lag phase, then a middle phase or log phase, and finally the negative accelerative phase a stable condition until an equilibrium is attained. And it develops a sigmoidal or S-shaped growth curve. The level beyond which no major increase can occur is referred to as saturation level or carrying capacity. Now, in the J-shaped growth curve, that is dn by dt equal to Rn, where there is no environmental resistance, the particular population can grow exponentially. This increase in population is controlled till a large amount of food materials exist in the habitat. And after some time, due to increase in population size, food supply in the habitat becomes limited, which ultimately results in decrease in population size. This will result in a J-shaped growth curve. So this is the equation. A J-shaped growth curve, which actually explains the exponential growth. There is no environmental resistance or carrying capacity. In the second condition, it shows a logistic growth curve. Here the growth can be regulated by the carrying capacity or the K. So the population forms a S-shaped or sigmoidal growth curve. So I think in this small lecture, we all have a basic idea about what a population is, what are the basic attributes of a population, and how they can be regulated. Thank you.